the physics video lecture, Physics 2A, video lecture 21. We're moving on to a new chapter. And you see I have a little demonstration object here and a tennis ball that we'll look at momentarily. So what we're going to be moving on to is chapter 7, and that's rotational motion, circular motion, gravity, satellite orbits, planetary orbits, all manner of great stuff. What I'm going to do is save the rotational motion for the end of the chapter. We're going to pick it up and run with it into chapter 8. But I'm just going to write down here rotational motion, and I'll check that off very shortly. Then we're going to do circular motion. So we're really going to start the bulk of this off with circular motion. Of course, rotational motion and circular motion are related. Okay. So here I have a plexiglass disc, okay, and it can rotate about an axis. Think of the axle coming straight at you in the middle here. And I just want to bring into play some definitions. And so we draw a large circle. We can characterize it by its radius. And we can look at an arc length along the circumference there. There's another radius. And we can define an angle. Okay. Now the way this angle can be defined, it's a dimensionless quantity as a ratio. It's S divided by the radius. So there's a dimensionless quantity because meters divided by meters is dimensionless, okay? Now, furthermore, okay, so let's make sure we write this down. We have our circle, if we didn't know already. Now, what are the units? Well, the units are a dimensionless unit called the radian. It's dimensionless by its definition here, but by its definition off of this circle of radius r, we can immediately see that 2 pi radians equals 360 degrees. So in these next couple of chapters, we'll be using radians often, and we can see the definition right there. Okay. Now, here's another interesting thing about our demo object. You see that black triangle, and this ruler has been cut to have the exact length of the radius of this disc. Okay, and if you lay it across the top, we see that there's the perimeter. Okay. So 1 radian would be when S is equal to R. Okay, that would be 1 radian. Good, otherwise this is just a conversion factor. No big deal. So when we get to rotational motion, we'll be talking about the rotation of these rigid bodies as a whole, and we'll develop the theory of rotational motion. What we now want to do is talk about circular motion. So there's a red dot here on the edge of this, and if I spin this one time around, it'll go in a circle. Okay, so we're talking about the circular motion. So I've dealt with rotational motion as much as I'm going to for the moment. We're going to talk about circular motion next. Circular motion. And the example would be the red dot spinning around there, or if I had a tennis ball on the end of a string, there's a circular motion there. I could whirl it around above my head. Okay, and this is what we're really thinking of, an object that's going in a circular, along a circular path. Good, so let's send this up here. And we'll jump right in to what's referred to as uniform circular motion. Uniform circular motion. So again, we draw a nice large circle, and we imagine we've got some object there, some point, and it's going around counterclockwise. So the first thing we note, okay, we've got our circle of radius r, and the positive orientation is counterclockwise. That goes for rotation as well as just for, say, revolutions. So counterclockwise is the positive orientation. And if we say uniform circular motion, so I'll just write here, positive orientation is counterclockwise. Counterclockwise, yeah. So what does uniform mean? Uniform means constant speed. Okay. So the speed of this thing as it goes around is constant. And of course, speed is just distance over time. And the distance would be around once would be 2 pi times the radius. And the time we're going to call capital T. So that's the circumference over the period of revolution equals circumference, that's a length, and this is the period of one revolution. Okay. So we use T for tension often, but now we're using it for the time it takes to go around once. Okay. So that's what we mean by uniform. It's constant, and there's a definition for the value of that constant. Okay, so things are going around and around counterclockwise. What about the velocity? This is the speed, okay? Here I'll underline speed in red. This is the speed. What about the velocity? Question marks, 2 question marks for the velocity. What about the velocity? Now the velocity is always tangent to a curve. So that would mean the velocity is always changing. So let me go ahead and draw a couple of points here at the middle. I'll call this point A and this point B, so we're going counterclockwise here. The velocity at point A is tangent to the curve. A red velocity vector would look like that. Okay, and the velocity at point B would be like that. So the length of these two vectors would be exactly the same. You know, if we were scaling these correctly, did I do that? The length of these velocity vectors is the same, but their direction has changed. The reason the length is the same is because the speed is constant, but the direction has clearly changed. So let's put this in words here. Velocity is always tangent to the trajectory. We learned that earlier. And here we have an example of it. So therefore, velocity is always changing on this type of motion here. Okay. On this uniform circular motion, the velocity vector is always changing. Therefore, uniform circular motion is accelerated, okay, because a changing velocity is an acceleration. So it's accelerated motion, and I'll just put right here, we could even say acceleration is equal to delta V divided by delta t, right? And the limit for calculus, but otherwise is the change in velocity over the change in time. So our next task is to figure that out. Because now we have a clear fact it's an accelerated motion, but what do we need to know about this vector? We need to know its direction and its magnitude. So that's our next question, direction and magnitude. A couple of ways to do this. So our next question, are we still numbering things? Sure. 4. Direction and magnitude. Magnitude of acceleration vector, question mark. What is the direction and magnitude of the acceleration vector? Well, that picture's already up there. We'll do a new one here. So this is a construction. We have to try to make this as accurate as we can. So I'm going to draw these 2 arrows here. Those are the velocity vectors for those 2 respective points. There is, see if this blue shows up, there is a certain arc length associated with that. I'll call it delta S this time, same as the S above, delta S. And these are our V sub B and V sub A. And this is the radius R. Okay. So the delta V A equals delta V divided by delta T. So we're going to do our little vector arrow addition. The delta V is the VB minus VA divided by delta T. And the VB is pointing in this direction, and the negative VA is pointing in that direction. Okay. So this is V sub B plus negative V sub A. And if we add 2 vectors like this, the resultant is in the down direction. What that means is the acceleration is towards the center of the circle. I could do this construction anywhere, I would get that same same result. It has nothing to do with the down as in up and down. It has to do with the difference of these vectors points towards the center of the circle. So, we could divide this by delta T. And so what we have is acceleration is directed towards the center of the circle. Directed towards the center of the circle. I have plenty of other proofs of this as well. It's an interesting point. And it is called, let me put, centripetal acceleration. So centripetal acceleration means acceleration towards the center. So that's the first important point. So we have the direction. Okay, what about the magnitude? Let's see, I think we can fit the magnitude right here if we're careful. 1, 2, 3, 4, so 0.5, the magnitude of the centripetal acceleration. And remember the magnitude, we use the absolute value signs, okay? So magnitude of centripetal acceleration. Now this is an interesting construct, and the geometry is all up there. So what we have to do is, right, A is going to be the magnitude of delta V over delta T. So now we have to find this delta V here. And this delta V, its magnitude, we can get with the construction here. if we look at, so I'll put a question mark here. So if we label this triangle V, V, and delta V for the change in V, okay, then by construction, we've got this delta theta in here. Remember, the delta S was the perimeter, the delta theta is the angle that goes with it. By construction, we have the same angle. So for this construction, we have, by similar triangles, now it's not all going to fit on this board, but that's okay. By similar triangles, delta V is to B as delta S is to R, okay? Delta V is to B as delta S is to R. Okay, good, so. Got that there. So here we go. We're looking for the magnitude of that acceleration. Once again, delta V over delta T. Now the delta V from this equation here, cross multiplies V over, we can say it's V delta S divided by R, and I've still got my delta T there. So that's V divided by R times delta S over delta T. But the delta S over delta T, remember we're going around this counterclockwise, that is just V, right? The distance traversed over that delta T. So that is the V, let me just point the arrow there, that itself is equal to V. So what we have is for the centripetal acceleration, V times V divided by R. This is a world famous and important result. Okay. The magnitude of the centripetal acceleration. So now it is on these boards, right? The direction towards the center of the circle. Okay. And the magnitude, the speed squared divided by the radius of the circle. And important is that this result is just obtained with a little piece of the circle. We didn't actually have the entire circle. The construction just involved this little piece up there, which we'll make use of in a moment. So those are really important results, and I can erase this now. What about the force? So next, Newton's law. Well, Newton's law, we say net force equals mass times acceleration, and we know it's a vector equation. So now in the case of uniform circular motion, we'll have F centripetal is equal to mass times A centripetal. Okay. So for uniform circular motion, Newton's law says this: the force that points to the center is equal to the mass times the acceleration. Okay. And so to complete this, where A sub C V squared divided by R, comma, directed towards the center. Towards the center. So this is our new formalism. Many excellent applications it will do. first a demonstration to make this all completely plausible. Namely, this ball here, I don't know how well this is going to show up on the camera, but I'm whirling it around in a circle, and since it has a string here, I'm feeling tension in the string, okay? This thing's going in a circle, and the tension is along this flexible string. So where is the tension towards? Towards the center of the circle. Here, let me do a slow motion demonstration. So this thing's rotating or moving on a circular arc, okay, even as a pendulum. This is clearly flexible, so the force acting on this thing is towards the center, okay? Towards the center when it's doing the circular motion. Now what I like to do when I have a class is whirl this thing over my head, pretty much over the heads of the class, and then I let go at an instant when the ball is directly towards the class. So if the class were here, gotta be careful with this. If the class were here, if anything went wrong, I would hit the class, and in this case, I'll hit the camera. So, but what happens if I release the ball when it's towards the class, and in this case towards the camera, is that it flies off to the side, okay? It's the instant I release it, that force is gone and it flies off to the side. So I'm gonna draw that as a top view, as a demo that we wish we could have done. We'll call this the demonstration we wish we could have done. Demo tennis ball on string. While we're at it, we wish we could have had a top view. Okay, so we got the top view. So the ball is whirling around. Let's do a better circle. Okay, we can get a slightly better circle here. So here's the string. The hand is holding the string. There's the tennis ball right here. And then the tennis ball. Here I'll do 3 points. A, B, and C, okay? A, B, and C, and I'll remind us the velocity here, then it's here, then it's here. So it's the tension in the string that each time is keeping this ball on its circular path. So if at the instant that it's up here at C, remember this is a top view, we're just looking down on it. If at the instant at point C here, I let go of the string, now the only remaining force on it, ignore gravity, the only remaining force on it is what? There is no remaining force on it. The string's gone, and the force-free object just goes on in a straight line. Goes on in a straight line, so as long as the string was being held, it's going in a circle, there's tension in the string. The instant that I let go, it just continues on in its straight line. So yeah, you're welcome to try that out. Drill a hole in a tennis ball or something, tie a string to it, whirl it around, and let go. Yeah, and as far as this goes here, FC is the tension. So the tension is equal to mv squared over the radius. Okay, good. Let's see if we can get a bunch of examples now. Ah, yeah, perfect. Tension. Okay, yeah, so it's unfortunate that I'm using tension T and period T with the same letter, but you just gotta figure it out. Okay, so now let's give examples of centripetal force. And I already have one. So one example is this tension in the string. So let's just write it down. The tension in a string, okay, tension in the string will certainly hold something along a circular path. Now a great demo object we have, but I can't show you, is a normal force. So what we have here backstage, we have this plexiglass cutout with a circle, and the other one, I'll draw the circle and show you what we have here. It's a circle that is actually cut out like this. Okay. So we have circle and a semicircle here and a plexiglass cutout. What I usually do is I put this on the overhead projector and project what's going on. A ball will roll around here in a circle, okay? On this one, let's draw this a little better because it's so important. So on this one, the arc come out like that. And if I roll the ball in this one here, it rolls around. This is flat on the table, and the instant it leaves the plexiglass cutout, it just goes in a straight line. Okay, that's the same as cutting the string. But in this case, since it's a plexiglass thing with a hole cut out in it, we're talking about a normal force. And what's keeping the ball in its circular motion is just the normal force. Here, you've got a normal force until you have no force at all, and it just leaves in a straight line. Conceivably, I could bring this in next time, but I'm kind of limited to this setup right here. So normal force, tension in the string. The third example we're going to do is friction. And the example will be an automobile on a mountain road. So friction, parentheses, mountain road, or just a curved road. Curve in the road. It doesn't have to be in the mountains. Any old curve will do. Okay. Now this is where the generality, let me get this in here. This is where the generality of our construction comes into play. I'm going to draw a top view of a curvy, windy road, and we'll analyze that. So good. This is the road, and it goes around a curve like this. So here's a tighter curve, bigger curve, and here's the center line. And we're driving, okay, right lane, and we're going to go around here, okay. And you'll notice the curvature of the road is changing. When we're here at point A, call this point A, we're dealing with a section of curved circle, something like that. So we have a piece of road that has about that curvature, so there's our radius of curvature. And when the car is right here, the centripetal force is towards the center. You go around, you got a straightaway, and then when we're at this point here, which I'll call point B, the center of curvature is now, it's a much larger curve, okay? So now I'll call this R sub A, and this will be R sub B, and the car is right here, and the force is towards the center of curvature. So we've got a car on this winding road. Force is towards the center of curvature, which I think I've illustrated pretty well. In fact, if you were going around this road right here, say it's in the mountains and there's ice on the road, you're going to skid out, okay? You're going to lose that friction between the tires and the road, and in fact, you're going to, y'all just imagine there was some ice right there. When you hit that patch of ice, you're just going to keep going straight. You're going to lose the friction of the road. So force is towards the center of curvature, and force is provided. Force is due to friction. Friction between the tires and the road. So if we were to do F equals M A centripetal, say it's point A or point B, it doesn't matter, we would say the friction, which I'm often using lowercase f as before, is equal to mv squared over r. And I could even say that this is mu times the normal force, mv squared over r. So that's how we set up a problem with Newton's law with circular motion. Towards the center of curvature, and you have to identify what that force is, and then you have to set it up like this, mv squared over r, mass times acceleration, mv squared over r. And in this particular case, you'll see the masses cancel and you get some interesting result. So forces towards the center of curvature, that's when it's a centripetal force. So now we have a bunch of examples, right? We have the tension of the string, we've got the normal force, we've got the friction for a car on a mountain road, or just a car going around any turn. And by the way, this result, let me check the time first of all. Yeah, no problem. This result is kind of useful in terms of your knowledge and skill as a driver. So I'll say a little bit more about it. So now we have the coefficient of friction is equal to, times G is equal to V squared over the radius of curvature. And this, of course, is the maximum speed. If you go any faster than this with the same coefficient of friction, you're going to cut loose. You're going to, right? You're no longer going to be held down by the friction, or held on your curve by the friction. So yes, okay, this is worth analyzing, right? We're not going to plug any numbers in. G is 9.8, we know that. Notice, if the radius of curvature gets smaller, okay, this entire right side is going to get larger, but your friction is not getting any larger, okay? When you go through a tight curve, you have to reduce your speed, okay? If you go through a large curve, you can go faster. So you've experienced this, the tight curve, you can't go through as fast as the large curve. And the other interesting thing is the sensitivity to the speed. If you double the speed through a given curve, you need 4 times as much friction. Okay? Double the speed, square the 2 gives you 4. So if you double the speed, you need 4 times the friction. So I'm going to put that as a note because these kind of relations are, of course, pretty crucial. If you double your speed, you need 4 times the friction. Well, getting 4 times the friction is pretty hard, so you can't just double your speed arbitrarily. But this relation here is pretty important. Good. So force towards center curvature. And now I'm going to set up 2 or 3 problems that we'll have on the homework. Good. Consult the clock again here. Okay, yeah. So these are going to be homework problems. And I'll look it up in the book in a minute. But this is a good problem. The idea is we have a roller coaster. And we draw us a nice roller coaster. Say we come up here and then go down and up over the hill. Okay, so start here. And it's going to be a frictionless roller coaster, so we can certainly calculate the speed depending on how high it is. Start here from rest, right? Now the thing is this, down at the bottom here, we're on a piece of circular arc, and up at the top, we're on a piece of circular arc. So let's look at the force diagram. Down here, I'll call this point A, and I'll call this point B. So at point A, we have mg in the normal force. And at point B, we also have mg in the normal force. But the difference is that this time, and at point A, the normal force points towards the center of curvature, and at point B, the weight points towards the center of curvature. So here's what we have for our problem. At point A, we have, and in fact, let's always just write Newton's law down. It'll do us no harm. Okay. So now at point A, our net force is N minus mg. And that's going to be mv squared over r, which I can call r sub a, right? At point B, we're going to have to write minus n plus mg. Because the mg is the positive direction. The positive direction is towards the center of curvature. Yeah, in fact, you know, I didn't write that up there. I wrote forces towards the center of curvature. We also have to say the positive direction is towards the center of curvature. So these are similar, but actually two somewhat different r sub b. I'll make that note right here because it's an important one. When you set up Newton's law, important note, the positive direction is towards the center of curvature, and I did exactly that in both of these expressions. So we have the positive direction is towards the center. Towards the center of curvature. So yeah, then you have your recipe. You figure out where's the positive direction, Newton's law, boom, 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 and then you can solve for n unknown in each of these. What's really interesting about the second one is that when n becomes 0, if you're going fast enough, you're actually going to become airborne, okay? And your roller coaster has to have wheels on the top and bottom of the track to make sure that doesn't happen. Okay, roller coaster, I'm going to write also pendulum. You can imagine the pendulum would be set up the exact same as this here, except instead of a normal force, we would have a tension. So now I'm going to look up what problems I want to have you guys do. The roller coaster one I'm looking at right here. Fantastic. And Actually, these are both really good. So this is homework 21, I believe, right? Are we in 21 today? Yeah. So let's send this up here. These are all done in a really similar manner. So homework number 21, I think you'll like these problems. We're in chapter 7 and we're looking at problem 32. This is the roller coaster. Now a snowboarder in a half pipe, you're going to see it's very similar. I'm going to write this one down as well, 28. And that one is exactly the same as a pendulum. I just can give you a third one. We should be in good shape here. Oh, and by the way, always ignore the numbers till the very end. Okay? You want to set these up analytically, just like I've done. I've already set them up for you, and just don't bother with numbers until you're ready to plug them in at the end. And I think we'll do 27 as well. Okay. So this one here is a roller coaster. And this one is identical to the bottom part of the roller coaster where you have a specific speed that you can get as well. So these are just like the roller coaster. And this one here is interesting as well. It's this tension in the string. This one I'll give you a little more background. So imagine you had a tabletop and you have a frictionless tabletop and you have a little mass that can slide without friction, and it's connected to a string, and you can hold the string right down here with your hand, okay? And so this thing goes in a circle. Okay. The point is the centripetal force is the tension in the string, and the tension in the string is how much force you're exerting down there. So I believe, yeah, and again, ignore any numbers until you've set this thing up. So what they gave you in the problem was an m sub 1, and they said there's just another mass here, m sub 2, hanging in place. And this thing's whirling around, so the tension in the string, I'll help give it away here, the tension in the string is just going to be m sub 2 times g, right, the weight of this thing. But this thing is whirling around in a circle, there's a radius r, and there's a speed that goes with it as well. So you use the centripetal force formalism on the top here, and the tension which is causing it, I don't have one of those written down. The tension that's producing it is m2 times g. Okay, so this is a great problem as well. And with these three, I think you'll enjoy these. And if you have, this goes for always. If you have certain questions about homework problems, I'll always talk about them in the lecture if someone gave me a heads up in the emails. Good. So see you guys next time.